Czy jest szansa na
I just
nagłośnienie?
said that we had unusual opportunity to have you as a guest here, and that I will say something in English now. I have the pleasure of introducing more than just Professor Penrose. I want to tell you that Professor Penrose is here because of his almost 2 years collaboration with Professor Meissner. Professor Meissner wrote a paper, Professor Penrose read it, got interested, they started talking. This is the typical way it goes. If you do something, maybe somebody will get interested and then things progress from that. So now I will like to ask Professor Meissner to introduce Professor Penrose.
Okay, I'm secondly trained. Already Professor Penrose had the lecture today in the morning, but none all of you were there. So I don't think I have to introduce Professor Penrose too much, but I think everybody knows as a creator of twistor theory, from Hawking-Penrose theorems, from Weyl curvature hypothesis about the initial conditions, about the Penrose tiling, so the one that is preceded the quasi-crystals by several years, I guess. Yes. He's either founder or discoverer or many ideas in gravity, and not only in gravity, in art as well. So I leave to you all the questions and the answers, Professor.
I'm not quite sure I can remember who I'm supposed to introduce now.
I'm here just to moderate questions.
Okay, fine.
So, someone would like to ask the first question? Please, raise your hand.
So ask a second one.
Well,
Okay, so
there's a question there.
Yeah, I mean, I can be the first one, why not? So, about the quantum brain hypothesis, let's put it this way.
It's a different topic altogether, but go on.
Yeah, and regarding its critique, what do you think about it now? Because the theory or the postulate has a few years.
You're referring to books I wrote some while back.
Yeah.
For example, The Emperor's New Mind and Shadows of the Mind. Well, there have interesting things have happened. And I should explain what the book was about, I suppose, because not everybody will know. But it's really, the origin is not to do with quantum mechanics, although that it had to do with whether there is something going on in the brain to do with conscious experience or conscious activity, which is not computationally controlled. See, it's a current view, which is very popular these days, since electronic computers have become so powerful and so impressive in what they do, that's what we do when we think. And that the brain is basically an electronic computer in biological form. I've tried to argue that there is something else going on in conscious activity. Maybe a lot of the activity in the brain is of the nature of a computation, and that may be the way to understand it. But conscious understanding, I claim, is something which cannot be explained computationally. And the original reason for thinking this has to do with the famous theorem of Gödel, which tells you not in the form he originally presented it, but more in the form that Turing later on encoded it, is if you have a system of rules of proof. Suppose you have a class of theorems that you're interested in proving, and these can be just things about number theory. They can be things about numbers like Fermat's last theorem, or such things of that nature. And one might have a set of rules, which if you follow these rules if you follow them consistently, obeying the rules, then the conclusion will always be something you believe. That is to say, it will constitute a proof. And then what Gödel shows, or Gödel and Turing, is if these rules have a computational character, if you could put them on a computer, then you can always construct a statement which, if you believe that the rules only prove true results, this statement, you can say two things about it. One is it's true, and the other is that you cannot obtain it by means of the rules. And that is, I should say, not subject to argument. That's clearly established. See, what people often think Gödel's theorem says is that there are things which are unprovable in mathematics. It doesn't do that. It shows you how to construct a statement that is not provable by the means that you have laid down, if you trust those rules that you have laid down. So it's simply explaining that our understanding of what's true in mathematics is not derivable simply by rules. Because if these rules are things which you believe and trust, it shows how you can go beyond the rules and find things which you must also believe by virtue of your trust in the rules. Now that's a bit complicated, but to me it's telling you that the way we believe truths in mathematics is not following rules. It's because it's your understanding of the rules and your understanding of what the rules mean which tell you whether you believe the results. And so what does that mean? What's understanding? Well, it's not computation, I'm saying. And it's certainly the way we use computers these days. You say, well, you use a computer to calculate things and work things out. But how do you know that to trust the conclusion that comes out if it's, say, proving something in mathematics? Well, you have to know that these rules that it's using are things that you trust, that you believe are true originally. And that is not something that it questions, it's just following the rules. It doesn't have the understanding that you put in. I don't really want to go into that in detail, and there's a lot of argument, and many people attack this point of view, usually because they didn't understand what I was saying, which I suppose is my fault, but I'm not sure, because I tried all over again in Shadows of the Mind. The original thing was The Imprisoned Mind, and then I wrote this other book called Shadows of the Mind, and in that book I tried to address all the questions which I thought were misunderstandings, and I made a whole list of these things, and still people complained and still didn't seem to understand what I was saying. So I'm at a bit of a loss there, so I stopped writing books like that. But I don't think the point is contradicted. The point is that the quality of understanding is something which is not rule controlled. I don't know what understanding is, but I do know that the normal use of the word understanding involves at least an awareness of what you're talking about. I mean, it wouldn't be reasonable to say that you understand something without being aware of it. So it seems to me that consciousness isn't necessarily involved in what you mean by understanding. So the thing, to me, is not a result of computation, is our awareness. So it's a bit of a mystery anyway what awareness is, and whether awareness is something that can come about through complicated calculations, which of course is the point of view which I expressed at the beginning, or is awareness something else? Is it something physical? You see, I think it is something physical, but if it's something physical, can it be something which is part of current physics? Now you see, current physics is very computational, and people can do remarkable things with, say, in astrophysics. You can work out what the systems, how they will behave, and you can see that they do behave in this way very closely. But these are following laws which are maybe Newtonian laws, or maybe using electromagnetic equations, Maxwell's equations. They're using laws that you can put on a computer. Now there is a question here, can you really put them on a computer? Because these laws depend on continuous parameters, whereas when you put them on a computer, you're using discrete approximations to those things. Now does that matter? Well, I don't think it does. I think that's not the point. It might be, so there's a question that one might consider there, but I don't think it's the point. I think that it's something else which is going on in physics which we don't understand in terms of current laws. Because current laws, even quantum mechanics, you're evolving the Schrödinger equation or something, which can be very difficult to do when you've got many parameters, but it's still a computational procedure. And so all these things, according to current physics, with the question that I raised a minute ago about continuous variables and can you trust your approximations, that is a question which is not a trivial question, maybe has to be considered seriously. But I don't think that, my personal view is that that's not where the problem lies. To my view, it's a gap in current physics which is being taken advantage of by the brain. Now this is a sort of very outlandish and outrageous thing to say, because I'm saying not only is the physics going on there, you know, very subtle and sophisticated, but it's something which is beyond the physics that we understand today. Now, I'm not saying it's something outside physics. I think a lot of people have a problem with this. They say, if I'm saying it's not part of current physics, am I saying it's something outside physics? No, I'm not. I'm saying it's outside the physics that we know today. Now, if there is a gap in the physics we know today, where is it? Now, you see, the usual view is there isn't a gap, you see. We've got these beautiful theories. We've got, okay, Newtonian mechanics works pretty well. In the places where it doesn't work, you've got relativity, special relativity, or general relativity if you need it. And then we've got quantum mechanics. Quantum mechanics, of course, goes beyond these other theories. But are there any gaps in quantum mechanics? Usually people say, well, quantum mechanics is so well understood, it's so beautifully confirmed by all experiments, why should I say there's anything beyond quantum mechanics that could be relevant in the brain? That's completely outrageous. It is pretty outrageous. I'm saying that quantum mechanics is A, limited in its scope. That's outrageous already. What's even more outrageous is I'm saying that this limitation is something that the brain is making use of. That's deliberately more outrageous. Let me talk about the first outrageous thing. Well, you see, quantum mechanics works, it's a beautiful theory, it works amazingly well, but it is only known to, and it works without exception. There is no known experiment which goes against quantum mechanics. However, in my view, that's not so surprising, because where the quantum mechanics goes wrong, and I think it does go wrong, is when you have large objects. And basically this was appreciated by Schrödinger when he introduced his concept of the Schrödinger's cat, as we call it, where you could have a cat which was dead and alive at the same time, and it would not be very difficult at all to produce an experiment where you have, say, a photon split into two groups, and this one triggers something which kills the cat, and the other one doesn't trigger it, and the cat's alive, and so you follow the Schrödinger equation, the cat is dead and alive at the same time. So that's the way the Schrödinger equation works. It's the way that part of quantum mechanics works. But then you say, well, that's not the way you use quantum mechanics, because what you do is you use the wave function to calculate probabilities. Okay, that is the way you use quantum mechanics. You use it to calculate probabilities. But that is not part of the Schrödinger equation. That's the other part of quantum mechanics. And these two parts of quantum mechanics are mutually inconsistent with each other. Now, that can be, arguments can go backwards and forwards endlessly. But to me, they are inconsistent with each other. The way you use quantum mechanics is there's one outcome or another. One is the dead cat, the other is the live cat. You will only find one or the other. You won't see the cat in a superposition of dead and alive, which was the whole point that Schrödinger was making when he introduced this thought experiment of the cat anyway. So he was trying to say, look, my equation, I mean Schrödinger's equation, is limited in its scope. And that's what he was pointing out. And Einstein agreed, and even Dirac agrees. There has got to be something beyond the standard rules that we have in quantum mechanics. Now, of course, people argue endlessly about that. I happen to think that where the limitation is in current quantum mechanics is when you have enough mass displacement that you have to worry about the effects of general relativity. Now, can be very small. You see, I can take this gadget and move it from here to here. There's already enough mass displacement there that if I had a superposition of the two locations, well, that superposition to survive for more than a tiny fraction of a second. So I'm claiming that there's something that's already gone wrong there. You don't usually worry about that because you don't do that solving the Schrödinger equation. You do that by classical physics or by bringing in the measurement part of quantum mechanics, which is inconsistent with the Schrödinger equation. I've been talking a long time about this question because it's a complicated question. But my argument is that there is a gap, and that this gap is not understood, and the understanding of it will require new physics, not just better understanding of current physics, but new physics. And that new physics is going to come in at a certain level which could well be relevant to the action of the brain. Now, it is a long, complicated story, and whether you follow this and disagree with me here or here or here or here, you might easily do so. But I'm just giving you my point of view. Now, my point of view is that when we consciously experience something or consciously choose something, there something which is taking advantage of the parts of quantum mechanics or the extension of quantum mechanics that we don't understand today. So what I'm not claiming is that the brain is making use of quantum mechanics. It's more outrageous than that. I'm saying the brain is making use of where quantum mechanics is wrong, which is a pretty wild kind of statement, so I'm not surprised people would disagree with me. But on the other hand, consciousness is a pretty strange phenomenon. It doesn't happen, as far as we know, all over the place. That gadget is probably not conscious. What's the difference? A huge supercomputer, there's no evidence whatsoever that it's conscious. People might say, well, you know, it thinks it understands or something, but there's no real evidence for that. It seems to me there is something very strange going on, which has taken many millennia of years to evolve and enable beings, not just humans, I'm sure, because even the poor cat, which has been putting into a superposition, in my opinion, has consciousness. And there is something going on there which is not understood, not just in detail, it's not even in principle understood according to the physics that we have today, and that we are going to have to develop that physics in ways which may seem not to have anything to do with it. I think we need to develop the physics anyway, quite apart from consciousness, but I am saying that I do believe that whatever is involved in consciousness, and we're a long way from understanding it, is something which needs to take advantage of that. Now you see, when I wrote the book The Emperor's New Mind, I had no idea what it could be in the brain. And I thought that by the time I had learnt enough to finish writing the book, I would get some insight into what it could be, and I didn't. So I had some rather weak thing at the end of the book, which I didn't really believe, to do with something to do with synapses or something. Anyway, let's forget about that, because one advantage about writing a book like that is not that it will encourage young people to learn about physics, which I certainly hoped it did to some degree, but that maybe other scientists in other fields might read the book and make a connection. And I think I was lucky that this did happen, because Stuart Hameroff, who is an American, what they call anesthesiologists, we call them anaesthetists in England, I think, but somebody who puts you to sleep when you're having an operation by giving you a general anesthetic. And unlike most of his colleagues, who didn't seem to be, I mean, they're very good at putting people to sleep, but they're not so interested in what they're actually doing when they put people to sleep. Whereas he was very concerned with what is really going on when you put somebody to sleep with a general anesthetic. And he considered, from various reasons, which I think were interesting, that these general anesthetics acted on these little tubes called microtubules. And microtubules are substructures of cells which are present, I should say, in almost all cells. They're not just in neurons, they are present in the liver or in your little toe, and not in red blood cells, but every other cell pretty well. So people will obviously raise the question, well, if it's microtubules, why isn't my liver conscious, you see? Well, it's not just presence of microtubules, it's got to be something to do with the role they're playing in neurons. Now, some various interesting developments have come about, which I think is your question. You're asking me, what's new, you're saying. I'm telling you what's old. So what's new is various experiments. First of all, there are experiments that have been performed by an Indian chap in Japan, he's called Bandyopadhyay, or something like that. And his experiments were concerned with looking at microtubules and trying to test their conductance when you put a voltage across with an oscillating voltage with certain very specific frequencies. And he finds that there are 8 different frequencies, that it suddenly becomes very conductive, but only at those frequencies. And these frequencies are not harmonically related to each other, so it's very strange. So he finds with these 8 different frequencies, suddenly, and they're very different frequencies too, suddenly the microtubule becomes very conductive. It's conductive in a way which is apparently not dependent on the temperature, or even more strikingly, on the length of the microtubule. So it's nothing like saying you've got a certain resistance, and the longer the tube, the greater the resistance would be, because of course the longer tube will have more resistance. But the resistance is more or less the same, no matter how long it is, and even goes down a little bit the longer the tube is, which is very non-classical. Now, he's been doing these experiments for a few years and having a lot of trouble with getting them published and things like this, which I suppose is an experience that some other people find in doing things which are a little bit against the grain. But he's gaining some, certainly in recently, he's done other, the original ones were done on individual microtubules in somewhat artificial conditions. He's now looking at live neurons and noticing these frequencies also play a role in axons and things like this. I don't know where it's all going. I don't know what the explanation for these conductance is. It doesn't look classical. It looks like something, I should say it's not superconductance. We're not looking at that degree of conductivity, but it's something which is quite unusual in biology. It's a conductance which is very strange and something very specific to these microtubules. I should say these are neuronal microtubules. They are brain microtubules, not human brain. They seem to be pig brain, but never mind. But he does seem to see these effects. There are, of course, arguments going on about these too. Okay, that's one new fact, which does seem to be very interesting. Another one relates to a question that I worried about when starting to think about these issues, was in the cerebrum, which is part most people think about when they think about the brain. You have, what is it, 10 to the, I can't remember how many neurons it is. 10 to 11, something like that. Okay, well there's another part of the brain called the cerebellum, which has about half as many neurons. It also has many, many more connections between neurons. That's the cerebellum, which, as far as we know, is entirely unconscious. Now, why is that part of the brain, which seems to be about as complicated, at least, if not more, and at least half as many neurons as the other part, is totally unconscious? If it was just to do with the numbers of them or anything, it's a huge difference. Now, some recent results have come about. This seems to be quite remarkable, in my opinion. Maybe I don't know how other people feel. But apparently there are 2 sets of experiments here, or 2 sets of observations. One has to do with people really tracking down where conscious experience does come in the brain. And you can track where the signals go in the brain, and they go this way and then that way. And it's only the 3rd time that consciousness comes in, apparently. So you have these movements of signals, and I don't know exactly what I'm talking about here, but it's something like that. And on the 3rd wave is where you get consciousness. And these are different parts of the brain. And the 3rd one is further down inside, at a certain level where you have a large number of these cells called pyramidal cells. They look like a pyramid and they're a funny shape. And these cells seem to be the ones where primarily consciousness is coming in. Cerebellum doesn't have any. So that would address that. Are the ones which are primarily of interest in relation to consciousness. Well, the only thing else I would say here is they do seem to be very, very prominently full of microtubules. There are very, microtubules are particularly prominent in these pyramidal cells. Now, I don't know where this is going. Also, there was another piece of evidence, which is that in studies which have absolutely nothing to do with the ones that Stuart Hameroff, my anesthetic, I don't know, I did mention his name, I heard before, Stuart Hameroff, nothing to do with his work, quite independently of this, have been exploring exactly the way in which general anesthetics, what parts of cells that do relate to, and what ones they basically knock out. And it does now appear that these are microtubules. This is very recent research, because there's been a lot of argument about that. So I think there is evidence suggesting that microtubules are important. Of course, a lot more work will have to be done to see how important is it really that they're the main place where consciousness comes in. There's also evidence that microtubules have a very peculiar role in relation to electrical conductivity. It doesn't directly tell you anything about quantum mechanics. I mean, what's that got to do with quantum mechanics? We don't know. The Anirban Bandyopadhyay's observations have a sort of feel of quantum mechanics about it, but it's not directly connected with what I was saying at the beginning. It's just that it looks as though there's part of a story which may be coming together, and maybe we'll see that we are having a role for large-scale coherent quantum mechanical effects in microtubules, which are the sort of place where you could build up enough mass displacement to influence the structure of the connections between neurons. So the argument basically is that neurons are not the place where consciousness is occurring. It's the neurons which are, if you like, magnifying the signals to a level where you can move your arms around, as I'm doing here, and things like that. So it's not okay. The story is developing. Sorry, that was a long answer to this question, which I hope was an answer, and I hope I can give you shorter answers.
Okay, so maybe next question.
This one.
We were talking about quantum mechanics. Actually, we have this beautiful theory which explains really a lot about what we are doing. We have beautiful mathematics which work in there. But if we try to ask some questions about axiomatics, for example, what is wave function or something like this,
Yeah.
we actually don't have any answers. We have interpretations, lots of them. Even you have one, if I remember.
Yeah.
I mean, lots of physicists use quantum mechanics without knowing why they use it and how to use it properly. Do you think if it is a problem for us and how to solve it?
I think it's a problem not so much for us. I mean, you might think that the problem is we don't understand it right and we can't explain it and so on. I mean, I think the problem is to a large extent in the theory. It's very hard to understand, not just mathematically difficult. I don't think it, I mean, people used to say general relativity is very difficult to understand. Well, it's not difficult. Okay, you've got to understand differential geometry and things like that in general relativity, but there at least you have a clear picture of how the theory relates to the world. You say, this theory describes how space and time is, it tells you how clocks behave, and these things, you sort of know what you're talking about. Whereas in quantum mechanics, as you're, I think, saying, we don't quite know what the wave function is. Is it really there, or isn't it? Is the world a wave function? I mean, sometimes people talk about the wave function of the universe, but it doesn't seem to be much like the universe we know. I mean, there aren't things in it, and so on. It's not quite. You want to be able to describe a world with things in it, like this, which are located in definite positions, and so on. Where you could a wave function is only. Well, people say, well, it's only describing probabilities of things. Well, it's not probabilities, because probabilities are real numbers, and wave function is talking about complex numbers. And these complex numbers are not probabilities. Well, the probability amplitude is what's that? Well, it's something which, when you square the modulus of it, you get a probability. Well, it's not really quite that either. You need to know what these things are before you know what quantum mechanics is talking about. And it's not clear what the ontology is. I mean, the ontology means how does that theory, the symbols you write down, how do they correspond to the world? And it doesn't have a clear answer to that question. I always often say, you know, I was asked once recently, and it was an Oxford debating place. Well, it wasn't one of the big debates there, but where the question was whether philosophers are useful, or philosophy is useful in science. And I made the point that, well, I wasn't sure. I think philosophy is useful. It's good to have your philosophy and to think in terms of a well-defined philosophy and so on. But whether philosophers are useful, I wasn't so sure. But I thought that the Oxford philosophers, for example, I would say, as far as I know, the philosophy department at Oxford knows more physics than anywhere else in the world, I think, as a philosophy department. And they really are very good at quantum mechanics and things like that. But the trouble is, as far as my concern is, that they have completely not done their job. See, what is a philosopher's job? It's telling other people, who are maybe not philosophers, when they're not being very consistent about things like ontology, you see. So they should be telling the physicists, look, you haven't got a clear ontology on your theory, do something about it. Find a theory with a good, clear ontology, what the thing actually means in the world. They don't do that. The ones in Oxford, they go along a route, I don't want to be rude to anybody here, but they go along a route which is, to me, a rather strange route, namely the many worlds view, where you say that Schrodinger's cat is dead and alive at the same time, and you come and look at it, and there's one of you that sees the dead cat, and another version of you sees the live cat, and you coexist in sort of separate universes, in a sense. Now, that's not an uncommon view. This view is becoming more and more common, unfortunately, in my view. It's certainly very strong amongst the philosophers in Oxford. And rather than saying, look, this is where we're led, it's ridiculous, find us a better theory, which would be my attitude to what the philosophers should be doing. So, I don't know, this is relating to your question, I've not quite answered it. But I mean, I'm saying that the problem is that the physicists aren't very clear about what they mean. And it's not their fault, it's because the theory, in my view, isn't really quite right. And it's not that, you see, you could say, is the wave function real? Well, I rather tend to that view. I rather think that it is pretty real. You can ask a question of a wave function. You could say, I'm suggesting that you're this, you see. And you say, you can test it, and it will say yes or no to that. And if I've got my theory right, I can say, is this you? I mean, is the world this particular wave function? And you can, in theory, set up an experiment where it will say yes with certainty, that that is what it is. And so, to me, that gives it a reality, that the potential of testing it in that way, this was what Einstein had, an element of reality. It was Einstein thought quite deeply about these things, and he argued that this means that thing is real in a certain sense. It has an element of reality, I think is what he said. And I'm going along with that. The only trouble with it goes wrong was when you get ridiculous answers. And one of the ridiculous answers is with the Schrödinger cat, where the wave function seems to be saying that the cat is alive and dead at the same time, which to me is a ridiculous answer, and to Schrödinger was a ridiculous answer. So the thing is, it says to me, is that the Schrödinger equation is not right at that level. Something has happened to the world. Okay, the wave function was really correct, describing the world at one stage. It evolved to a certain stage, and then it did something which the Schrödinger equation does not tell you. The Schrödinger equation gives up at that point and tells you to look for probabilities. You've measured it, this thing. The measurement means that the measuring device has got entangled with the system you're looking at, and now the system has got bigger. It includes the measuring device as well. The measuring device can do one thing or another, rather than doing a superposition of one thing and another. So something has changed. So if you're allowed to say that the Schrödinger equation isn't completely right, when the system gets big enough in some sense, something else happens rather than the unitary evolution, which is the Schrödinger equation, then, okay, I don't see anything wrong. I mean, there are difficulties when you talk about non-local effects and so on. Okay, we have to worry about these things. But I can't see anything wrong with saying that the Schrödinger equation is real. It's just that the wave function is real, but it's not the evolution, which is given by the Schrödinger equation, is only correct up to a certain point. When mass gets displaced too much, and then you need to bring in something else which closely resembles the collapse of the wave function which we actually see. So I'm taking a very realistic in the sense of, philosophical, I'm saying, I'm allowed to say that the mathematical description that we're using up to a point is really describing the world. But the world at a certain point does not behave according to the Schrödinger equation. It behaves more like the procedure we use when we make a measurement. It's got to join up between those two in a nice way, coherent way, which it doesn't at the moment. You just have one end of the story and the other end of the story. We don't know what happens in the middle. But that's where I think we're missing a theory. So I think it doesn't seem to me that it's an inconsistent ontology. It's just that we don't have the right theory. So I think that would be my answer to the question. Yes?
I got a question which is a little bit in the middle
Okay.
of the previous.
Yes?
You told us about the new physics that we need to develop in order to somehow get rid of those inconsistencies.
Yeah.
But people from the ancient Greeks up to today, they always wanted to seek. We call it today the theory of everything, like our hair at the beginning and now this theory. Do you think that there is one? So do you think that we can construct the system, the theoretical system, which can describe everything in the future and in the past and
Well, I
at
wouldn't
this moment?
necessarily expect that it would.
It's just a
Oh, is it?
microphone.
It's not really so. Okay. Sorry, I hope that's better.
Right?
It's all right for me. Is it all right at the back of the room? Is the question.
Okay.
Yes, that's a good thumb up. Thank you. Well, of course, I wouldn't like to predict the future in two senses. One of them being that I don't demand that if we had a theory of so-called everything, which I don't like the term because it's, I think on the one hand it's giving me physicists a bit too much say in what means everything. I mean, it's not really. Okay, let's talk about physics. I mean, that's what we're going to talk about here. We certainly don't have it yet, in my view, because there are huge gaps, and I think the hugest gap so far, we may find huger ones later on, the hugest gap so far is in quantum mechanics, is that it's not finished. That we have to complete the theory in a way which allows the measurement process to be part of the theory, which it's not at the moment. So I'm talking speculatively about things which we certainly haven't got to that stage. You're really asking me whether I think there ever will be such a theory. Well, you see, it could well be that such an attempt at such a theory, the best we can do, might still not be predictive. You see, it could well be that it's indeterministic in the way that current quantum mechanics is, and that the theory only tells you the deterministic part of the scheme. It doesn't tell you anything about where there's freedom in behavior, which there could be. Now, this freedom could be entirely statistical, or it could relate to what we call free will, and so on. You see, there may be, relating to the first question, whether there is something going on in the reduction of the state which is related to what we call free will. Maybe there is something there which is freedom in the physical laws. I don't want to say anything about whether I believe that or not. I'm just saying that that's a possibility. There could be freedom in the physical laws, and it could be that that freedom, whatever it is something which is being exercised in our free wills, if there is such a thing. I'm not, as I said, making a claim one way or the other. But I think your question was somehow implying that an ultimate theory, so-called theory of everything, would be one in which the future would be exactly predictable. And it might not be. You see, it might be that it's a theory of everything that we could have a theory of and still not be a theory of everything. So that's a possibility. And I suppose I'm slightly swinging to that view just recently. I don't think I liked it very much previously. I'm not sure whether I still like it very much, but there is something in allowing that kind of freedom, certainly a statistical freedom, which allows you to do things which you're in trouble with otherwise. So it may be that there is something, whether it's purely random or whether there is something of the nature of some kind of control that conscious beings can exert, which is certainly the way we feel about things. Whether it's true or not is another question. So that's a very incomplete answer to your question. I suppose I think that there, ultimately, if we survive that long, which is not altogether clear, that we might get to a point where we will have a theory which is as good as it can be, in that sense. And if so, it would have to be of a very different character from physics that we know today. There's a question like that, yes.
So, in your book, The Road to Reality, you mentioned that it's hard for physicists to pursue unpopular ideas, not to follow the crowd. But it seems to me that there is an activity which is the attempt to solve the problems in critical phenomena in condensed matter physics by the string theory, via the holographic principle.
Uh-huh.
And what do you think about this? And
Well, I'm speaking from ignorance to some degree. I know there are parts of condensed matter physics where people say that they can appeal to the ADS-CFT conjecture or something, and there are parts of physics which seem to make use of some of these ideas. Maybe they do. I have nothing against that. It doesn't conflict with the sort of views which I hold on if you ask me about string theory and where I think it's going, well, I'm not sure where it's going with regard to physics. It certainly has made it's had a big influence on mathematics. And there are certainly instances where parts of mathematics have been revolutionized by ideas which have come from string theory. Or perhaps I should say from certain particular individuals who are string theorists. Whether that is string theory, I'm not sure. My main trouble with string theory is not the strings, which are a nice idea. I never had worried. I thought the idea, whether right or wrong, I thought it was a nice idea, certainly when I first heard about them. What I object to is the superdimensionality, the fact that one seems to be driven to spatial dimensions which are supposed to be wrapped up into tiny little knots and things like that, which I have a great deal of trouble with. I don't perhaps want to go into this here, but I think that I think that they are inconsistent with observations, mainly because of the potentially vast numbers of degrees of freedom which are present in these extra spatial dimensions, which are not the arguments that are normally given against these things having any influence on the outside world. Or I don't believe. I think that they will be catastrophic if those degrees of freedom were actually present. And so I have a lot of trouble with accepting the existence of higher dimensionality. So I think we have four space-time dimensions, and that if there are extra ones, they're not really space and time. There's some other. That's not the right interpretation. So that would be my view. That doesn't contradict what you've been asking me, whether these ideas have applications in condensed matter physics. It could well be that they have, but this is not part of the aims of the string theory. You've been trying to find a new way into understanding the basics of physics, which is quite different from finding the odd application here and there of certain ideas, good as they may be. And I'm not competent to judge them, I'm afraid.
Okay, so maybe next question.
I have a question relating to quantum mechanics.
Yeah.
So what do you think about the idea that wave function collapses with a certain probability dependent on time, which is dependent and negatively proportionate to the mass of the system, the way it's described? So basically, the more massive the object is, the faster, the more, how to say, per period of time, the probability is higher that the wave will collapse. And
yes. No, I would accord with such a view, but it's not quite that. Let me explain it a little bit more closely. I'm taking my object here again. You see, suppose I consider a superposition of it being here and being here. Now I calculate something. which is I look at the mass distribution in the difference between this location and this one. Maybe they overlap, so I move it only that much. And I take the difference between that mass distribution and that mass distribution. So one counts positively and the other negatively. It's an artificial distribution, but never mind. I then work out the gravitational self-energy of that difference. I call that quantity Eg, that E suffix G, which is the quantity which I interpret as the uncertainty in the energy of the state. So I'm supposing this thing is in a stationary state here and a stationary state here. Put it back. And so I'm trying to imagine that that superposition is also stationary in this place together with that place. But I'm trying to argue that that superposition is not quite stationary and that it will have a lifetime like an unstable nucleus whose lifetime is proportional to the inverse of this energy Eg. And this is quite a well-defined thing. If these two states are stationary individually, you have to be a little bit careful about this, because if you consider, say, a point particle and you move it to here, if it's really a point particle, then you see it's going to have this Eg will be infinite if you're not careful. But the thing is, that's not a stationary state, because the point particle state will spread out instantly. So you've got to be careful about things like this. But if you do it right, you can have a well-defined estimate of the lifetime of that superposition. And I think that was the thing you were mentioning to me. Now, there are experiments which are in train at the moment, which have been going on for some while yet. The one I know about particularly is done by Dirk Barmeister in Leiden and Santa Barbara. And he's been working on this thing for over a decade, maybe about 15 years so far. And when I was last in Leiden, which was about 3 years ago, I asked him, no, he spontaneously mentioned to me, he usually doesn't make statements like this, but he made a statement to me, he said, in 10 years, we'll have an answer. I saw him again 2 years later, and again, spontaneously, I thought maybe 10 years was a constant of nature, you see. 2 years ago, he said, in 7 or 8 years, we will have an answer. So I thought, gosh, that's fairly consistent. That was already about over a year ago now. No, about a year ago. So it's 6 years or 7 years, he claims we will have an answer. That's